We live in a curved space-time, Einstein tells us, but what curves it, and especially how? Watch the video until the end to discover Einstein's answer and his second famous equation. Master Panda! Panda. In the physics lesson series we've already started in the playlist, we saw that the space-time we live in is curved, having a precise geometric structure described by its metric g. It tells us how time will pass on our clocks, what the distance between objects will be, as well as the motion of a freely falling body or a ray of light. However, an essential point is the following. Who curves space-time and how is it done? Because until now, we have been the ones who build the metric in the few examples mentioned. Who is responsible for the curvature of the universe we live in? No, don't think about a creator. We remain within the framework of physics, and here we will look for the answer. To do this, imagine a universe with two bodies. One massive and the other small, a test body. In Newton's explanation, the massive body attracts the small one and thus sets it in motion. In Einstein's explanation, the test body, the small one, is not at all interested in the massive body. It has a trajectory determined only by the space-time metric in the region where it is located. Now let's replace the massive body with another one. If before the test body, the small one, had a certain trajectory, now it will change its trajectory because it is attracted by another massive body. Classically, we could say that the forces of attraction have changed. In Einstein's thinking, however, we don't have forces and we are forced to admit that the metric of space has changed. Time curve around the small body. Once this small body has a different trajectory, because only the space-time metric determines the motion of the test body, the small one, as we saw last time. Who changed this space-time metric around the test body, the small one, once I brought another massive body nearby? The answer can only be the following. The massive body itself. What do we deduce from this? That the space-time metric around the small test body, the one that determines its motion, has been modified by the massive bodies. This figure shows an example. Here I've depicted the two bodies in space-time. The space axis is horizontal and the time axis is vertical. In Newtonian mechanics, at the top of the image, the massive body on the left attracts the test body on the right. In the theory of general relativity, the massive body deforms space-time everywhere, including at the events where the test body is located. The test body will follow a time-like geodesic in this now curved space-time, and that's why it will move. It should be noted that not only space, but the entire space-time is curved. Of course, however, saying that these massive bodies are the ones that determine the metric of curved space-time is no longer enough. Unlike many of the assumptions made so far, this time Einstein had to pick up a pencil and actually calculate the equation. It tells us how the metric g of curved space-time is created by massive bodies for any coordinate system, t, x, y, z, even when chosen arbitrarily. What did he find? Who curves space-time? We might think it's the masses of massive bodies. After all, in Newtonian mechanics, they are the ones that determine the forces of attraction. However, Einstein was fully aware of the equivalence between mass and energy, which we also discussed in the context of special relativity. If they are equivalent, then we can just as well use energy to determine the metric tensor g, that is, the curvature of space-time. In the end, Einstein found that the most suitable description is given by the Energy-Momentum Tensor, whose form you can see here for stellar dust moving non-relativistically. It is a square matrix described in the four components of space-time, the first being time and the last three being space. In front of the matrix, we recognize the mass density ρ. Then, on its diagonal at the top, we have the predominant element, the energy density. The other three diagonal elements give the densities associated with momentum, and the rest of the elements are associated with a transfer of momentum and energy. Of course, like all formulations, this energy-momentum tensor matrix takes different values at different events in space-time. In the end, Einstein found the correct form of the equations. In them appears not only energy, as expected, but a much more complex quantity called the energy-momentum tensor. The new function is actually a generalization of energy and momentum, being described at any point in space by the energy density, momentum density, and the transfer of momentum along various axes. I have to say that the most beautiful description of the properties of the energy-momentum tensor I found in Landau and Lifshitz's book, The Classical Theory of Fields. I recommend it to you as well. The energy-momentum tensor of matter is then placed in the so-called Einstein equation, which shows us how energy curves space-time at each of its events. The equation looks like this. On the right side, we recognize the energy-momentum tensor of matter, T mu, together with Newton's constant, g, and the speed of light, c. The left side of the equation contains elements related only to spacetime curvature, now represented by the metric gmu. The indices are for spacetime. The other two elements come from this metric. The first is the Ricci tensor, denoted as Rmu. The second is the scalar curvature of spacetime, denoted by the letter r. For completeness, these two elements are calculated from the metric using the Christoffel symbol gamma, whose formula I showed in the previous episode. So what does Einstein's equation, which I'll show here once again, tell us? That the metric of spacetime, meaning its curvature, is generated by the energy-momentum tensor of the matter that exists in that spacetime. He was very excited about the equation he discovered because it has a covariant form. Simply put, the descriptions are made using tensors which, besides their matrix form, have well-defined transformation rules from one coordinate system to another. Einstein's equation, the most important one in the theory of general relativity, confirms that the laws of physics are the same no matter which arbitrary coordinate system we choose. Einstein was very excited about this aspect. That's why the new theory is called the theory of general relativity, as opposed to the theory of special relativity, which applies only to inertial reference systems. As I was saying, it took Einstein almost 10 years of intense effort to discover the equation that bears his name. However, there was someone else who found the same equation at the same time, but it took him less than a year. We're talking about David Hilbert. He was one of the greatest mathematicians of the last 2 centuries, with important contributions, not only in mathematics, but also in physics. He lived in the same period as Einstein, back when the latter was searching for the equations that now bear his name. Drawn to the problem, even inviting Einstein to Göttingen to hold a few seminars on the subject, Hilbert chose a different approach, one in which not the energy-momentum tensor plays a decisive role, but rather the principle of least action. In Hilbert's view, as a mathematician, the solution to the problem of the spacetime metric must be geometric, axiomatic, and general. After less than a year of searching, he found the correct equation, reportedly just a few days before Einstein, who had already been searching for it for many years. Although Hilbert was faster, he never claimed any priority over these equations because, as he himself admitted, he built his solution on the foundations already formulated by Einstein. However, Hilbert realized the importance of mathematics in the new physics that was developing, where mathematics was becoming more and more complex. There's a joke that he remarked, physics has become too difficult to be left in the hands of physicists. And that was today's lesson. If you want me to resume the physics lessons, write to me in the comments. You can find the old ones in the physics lesson playlist. Until next time, please subscribe if you haven't already by pressing this subscribe button right now. I thank those who support us on Patreon and here become channel members. I am Christian Prasura, you are cool, and I wish you all the best. Goodbye.